to talk about hydration of alkenes, but without carbocation rearrangement, which means without formation of carbocations, because if we form carbocations, we can't stop hydride shifts or methyl shifts from occurring. Once you've formed a carbocation, if it's capable of rearranging to make a more stable carbocation, it will do it. So we need to avoid carbocation formation. And we'd like to be able to do that in either a Markovnikov or an anti-Markovnikov sense. So let's take it as our substrate, a compound that would be prone to carbocation rearrangement, 3-methyl 1-pentene. And we know that if we did just plain old dilute aqueous sulfuric acid, we would generate from that the tertiary alcohol, 3-methyl 3-pentanol. And what we're interested in is coming up with reaction conditions that will allow us to make 3-methyl 2-pentanol, so Markovnikov addition, but without rearrangement. As opposed to Markovnikov with rearrangement. Or 3-methyl 1-pentanol. It would be synthetically quite powerful if we could generate any of those three alcohols, 3-methyl 3-pentanol, 3-methyl 2-pentanol, or 3-methyl 1-pentanol from the same starting material by simply varying the reaction conditions. So an anti-Markovnikov addition, a Markovnikov addition without rearrangement, or a Markovnikov addition with rearrangement would all be possible. It is possible. We simply have to change the reaction conditions. So to do an anti-Markovnikov addition, we will react the molecule with borane, usually as a THF complex. Because borane itself, because of the unfilled octet on boron, is unstable, it can usually be stabilized by forming a complex with tetrahydrofuran, which is then quite soluble in tetrahydrofuran, usually purchased as a 1 molar solution. And then in the second step, aqueous hydrogen peroxide, usually 30%, hydrogen peroxide, and sodium hydroxide. So basic is referred to as hydroboration oxidation. First step is the hydroboration. The second step is the oxidation with hydrogen peroxide. To do a Markovnikov reaction without rearrangement, the reagents are mercuric acetate in water in the first step, HgOAC2 in water, and then the second step, sodium borohydride in base. And this is referred to as oxymercuration. Demercuration. First step is the oxymercuration, and the second step with the sodium borohydride is the demercuration. So by doing oxymercuration, demercuration, we can get a Markovnikov reaction without rearrangement and generate 3-methyl 2-pentanol. And by doing hydroboration oxidation using BH3-THF complex, followed by 30% hydrogen peroxide and sodium hydroxide, we can generate 3-methyl 1-pentanol by anti-Markovnikov. So you can make note cards by simply putting in the reagents for the hydroboration oxidation to generate the primary alcohol, and the reagents for the oxymercuration, demercuration to generate the secondary alcohol, and add that to your list, the tertiary alcohol can be generated by simply hydrating with aqueous acid. So what we want to do is we want to think about the mechanisms of these reactions and why these reactions are able to generate the product that they're able to generate. And these mechanisms are fundamentally different from the mechanisms that we've talked about so far, where we have an electrophile that adds to one end, the less substituted end, to generate a carbocation intermediate at the more substituted end. Because in this case, we're not generating a carbocation. The electrophile is still attacking at the less substituted end, but it's going through either a 3-membered ring or a 4-membered ring intermediate. So many of these addition reactions, including oxymercuration, demercuration, or basically just oxymercuration. The demercuration reaction isn't an addition reaction. Many addition reactions, including oxymercuration, proceed through a 3-membered ring intermediate with a positive charge. And those 3-membered ring intermediates are analogous to a protonated epoxide. We already understand how a protonated epoxide is likely to react with nucleophiles, because we know that a protonated epoxide is going to proceed by nucleophilic attack at the more substituted end, where there's a larger partial positive charge. So if we proceed through 3-membered ring intermediates that have a positive charge in them that are analogous to this protonated epoxide, we would expect to see exactly the same regiochemistry. So the oxymercuration reaction goes through one of these 3-membered ring intermediates, and these are always anti-additions. All of them are anti-additions. It goes through a 3-membered ring intermediate because the nucleophile has to attack from the side where the oxygen isn't, right? Or in this case, the oxygen or bromine or whatever else is attached there. So these are anti-additions. And then there are another class of reactions give syn addition through 4- and 5-membered ring intermediates, inserted reactions. Membered ring transition states generate syn addition, and oxymercuration is one of those. So as we go through the mechanism of oxymercuration, demercuration, and the mechanism of hydroboration, hydroboration I meant here, as an example. So as we go through the mechanism of the oxymercuration, demercuration, and the hydroboration oxidation, we will be looking at the 2 other major kind of mechanistic classes of addition reactions to alkenes and alkynes, either generating a carbocation intermediate because the electrophile is hydronium ion, or generating a 3-membered ring intermediate with anti-addition, or generating a 4- or 5-membered ring intermediate transition state that generates a syn addition. So once we've gone through these 2, we will kind of have in hand an understanding of the major classes of addition reactions, and then it'll just be a matter of figuring out what other reactions fall into those classes. So the mechanism of the oxymercuration reaction. We have our terminal alkene, our 3-methyl-1-pentene, and we have mercuric acetate. Mercury 2 acetate. Mercury acetate is partially ionic, so it's always in equilibrium. With a monomercury or monoacetyl mercury cation and acetate ion. The electrophile is this so our first step, which is not really part of the addition reaction yet, so I'm going to call it step 0, is the equilibrium where a pair of electrons that used to be forming a sigma bond between mercury and oxygen goes with acetate, form acetate ion, and leaves behind the mercury cation. The mercury cation would be expected to be able to react, and since it's the electrophile, it should go to this end. Pi bond attacks the mercury. And we generate, as expected, a carbocation, but we don't really get a carbocation because mercury, in addition to having that positive charge, also has electrons. So instead of forming a carbocation, we actually form a 3-membered ring bridge where the positive charge stays on the mercury and a pair of electrons from the mercury donates in a concerted fashion. So we go through a 3-membered ring intermediate, not an actual carbocation. We can write a transition state for that. It has the mercury simultaneously forming a bond simultaneously forming a bond to both carbons of the alkene. There's no discrete carbocation intermediate. And because there's no discrete carbocation intermediate, there's no rearrangement. We're not going to get a hydride shift from this position, opening up that 3-membered ring. The 3-membered ring is relatively stable. The difference here is that instead of using a very small atom, hydrogen, as our electrophile, we're using a much larger atom, and that much larger atom is capable of bridging and attaching simultaneously to both ends of the double bond to form the 3-membered ring. This looks a lot like a protonated epoxide. We would expect the nucleophile, which is water, to attack now at the carbon that has the larger partial positive charge. That will be the one with the greater substitution. So we would expect to get the water, the nucleophile, attacking at the more substituted end, leaving the electrophilic mercury at the more substituted end. Sorry, at the less substituted end. Right, so we got our mercury acetate here at the 1 position, and we've got our alkyl oxonium ion now at the more substituted 2 position. So step 1 pi bond on the electrophilic mercury. For the three-member intermediate. And then step 2 is nucleophilic attack to open the three-member intermediate, reducing ring strain, or eliminating ring strain. And in this case, the nucleophile is water, because acetate ion is a weaker nucleophile than water, and acetate ion is there in relatively low quantity. All we need now to generate a neutral product is to do a proton transfer reaction to take the hydrogen off. The alkyl oxonium ion, and the oxymercuration is complete. And we have a secondary alcohol. So it's a 4-step reaction if you count the initial equilibrium, where the acetate ion falls off mercuric acetate or mercury 2 acetate to form this electrophilic mercury species. And then we undergo a nucleophilic attack on our electrophile, an electrophilic attack on the electrophile by the pi bond, so the nucleophilic pi bond attacking the electrophile, a nucleophilic attack to open up the three-membered ring, effectively irreversible because it releases ring strain, and then a proton transfer. That's the oxymercuration. So that's step 1, or the first part of the oxymercuration demercuration pathway. Step 2 is a magical reaction. You just say poof. This reaction occurs when sodium borohydride in the presence of base reacts to take off this mercury and generate the product alcohol. And it generates liquid mercury, elemental mercury, as the byproduct. Which usually coats the walls of the flask. If you're dissatisfied with poof as a mechanism, you can think of this as being a nucleophilic attack of the hydride ion from the borohydride on the carbon, pushing a pair of electrons onto mercury and acetate falling off. That would generate your neutral mercury, but it's probably not really the mechanism, right? It's probably not as simple as a nucleophilic hydride pushing these pair of electrons onto mercury and acetate floating off. There's probably more to it than that. But certainly this would help you visualize what's happening, and remember that elemental mercury in the zero oxidation state is the product. So this is a reduction reaction. It's reducing mercury from mercury 2 to mercury 0. So effectively a 2-electron reduction. So all told, there's 5 steps. If you want to include all of them, the initial pre-equilibrium, which I call step 0, this three-step addition process, pi bond attacking the electrophile, nucleophile opening the three-membered ring, proton transfer to generate a neutral product, and then the final step, the demercuration, that simply takes the carbon-mercury bond and converts it into a carbon-hydrogen bond. So that's oxymercuration. Demercuration, because the intermediate is a three-membered ring, we don't have to worry about carbocation rearrangement. same material. But this time the reagent is BH3. Generally as the THF complex or a dimethyl sulfide complex, but I'm just going to draw it as BH3 for simplicity. The boron is electrophilic. But now the nucleophile is actually attached to the boron. So we have the nucleophile and the electrophile present inside the same molecule. We have a partial negative charge on the hydrogen and a partial positive charge on the boron, because hydrogen is actually more electronegative than boron. Remember, hydrogen has an electronegativity of 2.2, and boron has an electronegativity of 2. So in this case, the dipole lies towards hydrogen. So the electrophile, the boron, will actually attack or be attacked by the pi bond, and it will prefer to go to the less substituted end. The electrophile always goes to the less substituted end, and at the same time, in a concerted fashion, the boron-hydrogen bond will attack the more substituted end. This is a concerted reaction. And is step one of the oxymercuration, or sorry, of the step one of the hydroboration. And the most of the mechanism for this reaction is actually the oxidation step. So we can go through a transition state that is starting to form a bond to boron, and simultaneously breaking that boron-hydrogen bond, partial negative charge on the boron. Pi bond is still partially there, and we're also forming the pi bond, and there's a partial positive charge on the carbon here, which is allowing the partially negative hydrogen to actually attack. Four-member ring transition state. Because it's a four-member ring transition state, and the boron and the hydrogen are being delivered by the same molecule, they have to be being delivered to the same side of the pi bond. So this is a syn addition. The nucleophile and the electrophile come from the same molecule. It's not possible to have a trans four-membered ring, right? That would be too much ring strain. You can't do that. So they have to come and they end up on the same side, boron and the hydrogen. The product is an alkyl borane. And you'll notice that there are still two additional boron-hydrogen bonds, which means there's nothing to prevent this reaction from happening again and adding a second molecule of the alkene through the pi bond attacking the boron and the hydrogen simultaneously attacking. And that can happen twice more, three successive hydroboration reactions to generate a trialkyl borane. The mechanism is the same in each step. It's a concerted four-membered ring transition state. But what it results in is a 3-to-1 stoichiometry alkene in borane. Or one molecule of BH3 can add to 3 molecules of alkene. You can form 3 moles of alcohol with 1 mole of the borane THF complex. These are stable. These can be isolated if you wish. But generally, when what one is after is the hydration product, one doesn't isolate the trialkyl borane. One simply throws in the sodium hydroxide and the 30% hydrogen peroxide into the same reaction mixture and isolates just the alcohol. So it's one step for the hydroboration part, unlike the oxymercuration, which was 4 steps, counting with re-equilibrium. But unlike the oxymercuration, demercuration, the second step, the oxidation step in this case, is not a single proof mechanism. It's a series of equilibrium steps involving a lot of acid-base reactions, and is more complicated than the mechanism for the actual hydroboration part. So we're starting with our trialkyl borane. And for simplicity, I'm just going to indicate the other molecules as R. R is this. So we actually have 3 of those attached, but we're going to be focusing on the reaction between the boron and the carbon. So let's just write 2 of them as R. And what we have in solution is hydrogen peroxide and hydroxide ion and, of course, water. The pKa of hydrogen peroxide is about 12. It's 3 orders of magnitude more acidic than is water because we have this electron withdrawing oxygen attached that increases the acidity of the hydrogen by stabilizing the negative charge on the other oxygen. So the first thing that's going to happen is an acid-base reaction. Which I'll call step 0, because it doesn't yet involve the borate species. And this acid-base reaction will be an equilibrium that lies way to the, let's take this hydrogen off. So I end up with a negative charge closer to the boron. Because the next thing that's going to happen is this negative charge is going to attack the boron. So that will generate water and the hydrogen peroxide anion, or hydroperoxide anion. And if we know that the pKa is 12 for hydrogen peroxide and 15 for water, 3 orders of magnitude less acidic, we can calculate the equilibrium constant for this reaction as 1 times 10 to the 3rd, which is effectively irreversible. So we don't really have hydroxide ion solution, we have a hydroperoxide anion. The hydroperoxide anion is nucleophilic, boron is electrophilic. It's happily lacking a formal charge, but it's unhappily not having a field octet. So step 1 here, or step 2 if you want to count the pre-equilibrium as step 1, is attack of the nucleophilic oxygen on the electron deficient boron. That's what boron does. Because it has an unfilled octet, it gets attacked by nucleophiles. But once it's attacked by the nucleophile, it's still not particularly happy, because the attack by the nucleophile results in a boron, which is a relatively electropositive element with a negative formal charge on it. And boron doesn't really like a negative formal charge. alkyl shift. This is the key step. It goes with retention of configuration. Which isn't relevant in this situation because we don't have a chiral center. But if we had a chiral center here, the oxygen would end up attached in the same position as the boron. So this alkyl group is going to move onto the oxygen and kick out hydroxide. We've seen alkyl shifts being driven by positive charge carbon pulling the electrons towards themselves. In this case, it's kind of a negatively charged boron pushing this pair of electrons that it doesn't really want onto the oxygen. Right, so one of the R groups, doesn't matter which R groups because they're all identical, is going to shift to form the carbon-oxygen bond that we have in the product. And eliminate hydroxide. That alkyl shift is not reversible. But boron has an unfilled octet. And boron's never happy. It's either unhappy because it has an unfilled octet, or if you give it a filled octet, it's unhappy because it has a negative formal charge. And it doesn't like either of those situations. Hydroxide is a good base. Hydroxide will attack the boron. So step 3 is another nucleophilic attack on electron deficient boron. To generate a tetrahedral boron, I dropped a carbon. Put that carbon back. The CH2 is still here in this product, and in this product, and in this product. Boron now has a negative charge on it. Doesn't really want to have a negative charge on it. You'll notice that this reaction is in equilibrium, which means the hydroxide could just fall back off to generate trivalent boron. This is going to happen 2 more times to generate 2 more OR groups, but I'm going to ignore that and not show it in this case. And then eventually what's going to happen is instead of the OH group falling off, the OR group will fall off to generate an alkoxide as a leaving group. There'll be 2 more RO groups attached because we will have done the first and second step, the nucleophilic attack of the hydrogen peroxide ion and the alkyl shift twice more. And we'll generate an alkoxide ion. And then a borate ester. In this case, it's a dialkyl borate. Means that we're working with an acidic hydrogen here. So the last step of this reaction, step 5 or step 6, if you wanted to count the equilibrium as an actual step, is an irreversible Bronsted-Lowry acid-base reaction, proton transfer, to generate eventually, this will happen twice more, and you will generate BO3, 3 minus the borate ion, which is the completely dissociated Since we're in base, we would expect sodium hydroxide to react with boric acid to generate sodium borate, Na3PO3. So the hydroboration reaction is a single concerted step, syn addition, generating a trialkyl borane, right, with three alkyl groups, three identical alkyl groups attached to the boron. And then the oxidation step is a pre-equilibrium, right, to generate the hydrogen peroxide anion from hydrogen peroxide and hydroxide ion. And then 5 steps, nucleophilic attack of oxygen from the hydrogen peroxide ion on the electrodeficient boron, an alkyl shift to take the negative charge back off the boron. That's going to happen, those 2 steps are going to happen twice to generate 2 more OR groups. Then we have a nucleophilic attack of hydroxide on the electrodeficient boron, a loss of the alkoxide leaving group, both equilibrium steps, and then finally an irreversible proton transfer where the alkoxide ion, which is a pretty good base, takes off the hydrogen boric acid, or in this case the dialkyl borate, to generate the primary alcohol. So we now have the ability to do a Markovnikov addition with carbocation rearrangement with dilute sulfuric acid, a Markovnikov addition without carbocation rearrangement by doing oxymercuration, demercuration, mercuric acetate in water, followed by sodium borohydride and sodium hydroxide, or an anti-Markovnikov addition where we use hydroboration oxidation, borate THF complex in the first step, and then basic hydrogen peroxide in the second step.